So what we are going to study, we are going to study mechanics. Mechanics, as you know, since your earlier classes, is the study of motion. Motion in the general possible sense, which includes both kinematics as well as dynamics. So once we are studying mechanics or motion of particles or a given particle or a system of particles, so we have to take into consideration what are the forces which are impressed upon that particle, which will give rise to dynamics regarding that particle, one particle, two particles, system of particles, and particle systems. Got the point? So, as such, the study of mechanics has been very much, if you just go to the historically, since Aristotle, people have studied mechanics. To say a brief about the thing that the jump from Aristotle, because we are going to study motion, and motion is basically by virtue of some forces which we define in the way we have studied in Newton mechanics. There is force is an agent which acts on a given particle, which is responsible for its motion. That force may be due to some property due to mass, due to charge, due to magnetic field, due to any force defined or undefined, we have not known. That agent is responsible for the motion of that particle. So we don't study motion in its intrinsic or innate sense. We study motion in presence of forces, or in absence of forces. If I restate the first law of motion or Galilean, that in absence of forces, the particle will continue to remain in its state of rest or in continuous motion. So force as a quantity is required to make this change or motion possible. So the idea of motion is somewhat intrinsically, it's somewhat related with how we define force. And the cut point of Aristotelian study of motion and Galilean study of motion was Aristotle thought a constant force is required to have a constant motion. But what Galileo said, that only force is required as an agent of change. Because if you use constant force, the body will move constantly. Got my point? Force as an agent of change, the way we define acceleration. So the idea of force and the way we state first of the body continues in its state of rest or uniform motion if there is no force. But Aristotle's idea was that you need force continuously to have motion. But according to this understanding of motion, that things naturally are in motion, if at all they are not disturbed by some external agencies, if you call force. So force as such is responsible for motion. So rest and uniform motion are somewhat synonyms. So and body will naturally uniformly move, or it will be in a state of rest. An agent called force is required to make change from a state of rest or from a state of uniform motion. What is the point? So this you know as part of whatever bit of history. Now what we are going to have a bit of maybe digression into this fact that we should also, there are some notions which we don't normally study in physics textbooks, but they are innately there, but they are in some form which is somehow absorbed in that thing. The notion of something called causality. And I'll add the notion of determinism. These are basically ideas from philosophy, but somehow they are part and parcel of physics. So we will see how later in the end of the class how this determinism is very much part of how we study mechanics or motion. Causality means what? Every cause is an effect. So if you observe an effect, it should have a cause, and the consequent effect can be traced to a second cause, or multiple causes, or got the point. So effect can be traced to a cause. So it's not that things come suddenly. So that cause can take it to the mechanical way, how we just say how we define force as an agent of change. If there is observable motion, something was responsible for motion, and that was some force. So you can understand causality, cause and effect. उर्दू इसमें क्या कहते हैं? उसको कहते हैं लगभग मालूम, है? What's the point? So you can see cause and effect as a thing. This is known as causality. And the other doctrine is also called something called metaphysics. One is physics, which deals with physicality of the things. The other is metaphysical, means things behind physical. So when you study physics, you are only interested in the physical part of the things. So why things behave that way? Why laws of nature are like that? So we don't normally address those questions. Those questions are addressed in philosophy or theology. God is responsible for it, or universe has some property, innate property in it. Got the point. So what is beyond physical, that is metaphysical. So there is one important property that is known as philosophy, that is known as determinism. Determinism means you have human mind has capacity to determine things. Given initial forces, we can determine future cause. What we can, if you have a position, you can determine things. So you can extend this idea to mechanics. If you have some forces, if you know initial conditions, we can determine where the particle starts and where it will end. The way you have done the problem in your 11th class. Given a force, you apply 5 1 Newton force, the particle will be precisely at that distance. 5 after 5 Newton, it will be there. You can exactly determine its space. So it's how you apply the principles of determinism in mechanics, in the idea of mechanics. But it's not necessarily we can determine. This comes to a larger question whether nature is deterministic or not. Whether nature is deterministic or maybe in mechanics we say nature is deterministic. But once we go to quantum mechanics, in your books you will see the sentences that quantum mechanics is not deterministic or indeterminate. There are various debates and chapters about it. Whether quantum mechanics is deterministic or before whether quantum mechanics is deterministic or indeterministic, whether mechanics is deterministic or not, we should somehow also have some feel of what determinism as a philosophy is. Got the point in broad sense. So now taking these things into consideration, what we are going to have our brief detour into the study of motion. Got the point? Any question? This much is clear. Now what we are going to say is so maybe the book which you are going to maybe I am going to follow mainly this book by Ian. It's a book, it's a short book, mechanics. Volume. But I'll recommend one more book as a prerequisite. Maybe in your earlier class might have studied it. There is another good book, Analytical Mechanics. By Finchhand. So maybe if this book is advanced, what I'm going to teach. So whatever, if you feel some difficulty, you can always take the recourse to this book as a base study. If you find some difficulty or some idea is not entirely clear, maybe there are some ideas which you might not have clear. So you can always take recourse to this book and jump to this book. What do you put? So there are many books. So I just now the course who are studying this classical means normal parlance. Classical means old, but the old, it is old, but it is not obsolete. One is old but obsolete. First to the you have to just sit down. It is old, but it has some relevance still. That has to be emphasized. That's why we are teaching this course called classical mechanics. Because for 300 years, this subject has been very much from 1600 to maybe you have to 1900. Maybe in 21st century, when people will write books or they will design courses, the proper way should be if quantum mechanics is a fundamental theory, then classical mechanics is a limiting case of that quantum mechanical theory. So, if quantum mechanics is a fundamental theory, classical mechanics is a. But as of now, for example, if for example you have some clothes, you want to enter into a which is a small kid. If you want, you cannot straightway put it into the hot water. You need something. So it's sort of what I should say, sort of a rehearsal. So world may not be entirely classical. You have to study world as a maybe nature as of now we study. It's more a quantum mechanical. But before entering quantum mechanical, so you have you adjust yourself or you just make yourself familiar or aware with some classical notions. So once you enter into quantum mechanical world, you know which clothes you have to just leave this thing. You have to leave those things which are not required there. But there is also something which of classical mechanics which is relevant. So there is also an interesting debate of classical to quantum mechanics. How we make transitions from classical to how to make transitions to from classical to quantum. But since we are interested only in classical, so there are some ideas or concepts in classical mechanics which have been relevant. For example, all the large-scale physics, solution mechanics, sun-body problem, earth-moon problem, fluid mechanics. So basic principles of mechanics are, or even all of the engineering, construction of bridges, roads. So the ideas of engineering mechanics are still valid. But as physicists, if you want to study theory, you can say classical mechanics as a limiting case of quantum mechanics. But once you study quantum mechanics, there is a further result called Ehrenfest theorem, where you study this thing, classical quantum mechanics. So it is old, but it's not obsolete. So we'll study at the end how you can jump from one phase to another phase. Now, the first chapter we are going to have. Equations of motion. So equations of motion you have been studying from 9th class. Given a particle, what are the forces of how the particle will continuously increase due to the second law. It's also a sort of differential equation. Now, before we are going to study differential equation, so you have some abstract notion. Abstract notion means you in mechanics normally you call as particle, and sometimes you call it as point particle. So point in your study of Euclidean geometry, when you study point is something which has no dimension.
Zero dimensions.
Zero dimension. So it's a very abstract. So how can you imagine? So when you say particle, it sounds. When you say particle, so you mean that it has some finite dimensions. It has some dimension. So you feel it. So the mathematical notion of point particle, or when you say a particle has some dimension, it has some extension, it might have some orientation along x-axis, y-axis, or z-axis. The way you study angular momentum, it can have various components. It can have various. And in your earlier classes, the components maybe if you have x, y, z components, 3 components. But if you have tensorial components, you can have components of how the components translate in space. How the components of that vector which change in space. So the notion of a given particle, how it is going to move in a space, it's also very much how we can relate the idea of particle to point particle, whether it has some extension, whether it has some orientation, and whether those orientations have components, and whether those components, how they translate or how they behave in presence of forces. So you can start from very simple thing, point particle, particle having mass, particle having extension, system of particles, or particles having the components. When the particle is in motion, the components may be different. For example, when the V, it can have Vx, Vy, Vz. Or, so normally, what are the coordinates? If you only take Cartesian coordinate system, we have only x, y, and z. But we in classical mechanics take recourse to something called generalized generalized coordinate system or generalized coordinates. So, and in this notion of coordinates, generalized, we have some notion called degrees of so degrees of freedom we know. So it's the orientation, how a particle is going to have a tendency. So what are the values you can, what are the possibilities a particle can have vis-a-vis motion? Got a point? It can move in x direction, it can move in one component, other component. What are the values, what are the possible values it can take? So if you have a coordinate system, normally coordinate system, we have only n is value, it can have 3 values only. But it can have in principle, it can be, why it can be n? For example, if only there are 3, because we are not interested only in 3 components. We can also interested in how the components transform in this space. The components of the components. It may not necessarily be 3. Maybe if it's rotating, if it is spinning, if it's translating, rotating linearly, so it can have many components, and it may not, the value of n cannot be restricted to 3. It can be, for example, you can say it can be n. But if it is in 3 dimensions, it can be 3n. degrees of freedom can be n. If it's in 3 n dimensions, if you take space as Euclidean, which has 3 components, so you have 3 n coordinate systems. अब ये है कि any s quantities which completely define, if I write it in the language of book, which completely define any s quantities, Q1, Q2, and Qs, which completely define position of system with s degrees of freedom. This is known as generalized coordinates. And these are the generalized coordinates. And if there is a derivative you can have. If there are two quantities, Q1, Q2, Q3, the derivative is 2 dots. The way we normally to make things not complicated, you have position and you have your displacement, you have velocity. Got the point? Simple. Now, what I was previously saying. So, if there are, if all the coordinates and the velocities of the system are specified, we say the system is completely determined. We say the system is completely. If all the coordinates. So, this is from this we don't see in books. It is something called determinism. It's a philosophy. So yes, the book uses the word completely. So it's inspired by this philosophy of determinism. We don't write determinism as a philosophy. So when he uses this, that we can specify, given initial conditions, given coordinate systems, and given velocities, if they are simultaneously specified, it is known from experience that the system. It is known from the experience that the state of the system is completely determined. We can determine system completely. But it's not always the case. For example, in case of if you have generalized coordinate system, so if you don't know the all the coordinates and all the velocities at a given point, because if the system is simple, the coordinates are 3, the way we have studied in the earlier classes. Because once there are different coordinate systems, there is a Cartesian coordinate system, there is a spherical coordinate system, there is a prolate, elliptical, hyperbolic. Why do you choose? There are 14 coordinate systems. Why do you go from one coordinate system to another coordinate system? The way you have studied, some problems in electrodics become easier. For example, that's why you take the course to spherical coordinate system. So in the same way, there are different coordinate systems, and how the components of those particles transform or translate in those coordinate systems. It varies from coordinate system to coordinate system. And you have to be conscious of the fact you have to study equation of motion of particle from one point to another point. So if there is a generalized coordinate system, it's not necessary you will know the coordinates and the velocities are simultaneously determined. Got my point? So that's what I'm saying. So for a given value of coordinate, the system can have velocities, and these can affect position of the system after infinitesimal time interval. So after infinitesimal time interval, with the generalized coordinate system, it may not be the same. It depends if the components depend upon coordinate system. If we can determine, so that is the way we would ideally want systems should be. And mathematically, this means coordinate fluid. Now I'll just stop. So you know in your earlier classes, these are known by the words called acceleration, velocity, and coordinates or equations of motion. Acceleration, velocity, coordinates. Or the other way is probably the coordinates is x, y, z, फिर velocity, then comes acceleration. So these are sort of maybe so for a given equation of motion, what we require? We require displacement, position, displacement, and this is
acceleration.
this is acceleration. So this will give us, in the broad sense, equation of motion. But for simple systems, if the system is determined, if you can determine the system, if the coordinates may not be generalized. If the coordinate is simple, the components are simple, which you have been studying. So it's a great, it's a problem in mechanics. How can choose a given coordinate system, and how can specify that coordinate system, and how we can determine the equations of motion, such that it should correspond to our determinism. We have to determine this, or it will correspond to our philosophy of determinism. Given initial conditions, we should know that where the particle has arrived, or where the particle is going to end. By these simple things, you not only can understand the motion of simple things, cars, particles, galaxies, many parts, statistical mechanics. So it's it's also how skill, how we can have a given particle and generalized coordinate system, and coordinate systems are required, how we can find these components vis-a-vis that coordinate system. So in the next few classes we are going to study the way you have studied classical mechanics. We are going to study classical mechanics via some formalisms like Lagrange, Hamiltonian, other formalisms, and see. Study this what? Study and this. Study what? Study what? Equations of motion. Okay.